Hello, today I'll be talking to you about the tool wear analysis section of the micromachining module. This is an important section because understanding what tool wear is, how it happens, and why it's important in micromachining is critical in developing effective work plans for later use in industrial production. Once you've completed this section, you'll be able to describe and analyze tool wear in several different ways. It's important to understand the performance of microtools and how they wear, especially in a production setting. If there is high tool wear, this leads to increased downtime of machines as well as higher cost of replacing tools. For example, the tools that are used in this lab are from performance microtools and cost between $40 and $60 on the low end and can range up to $100 depending on the size, coating, and material of the microtool. Tool wear is the gradual failure of cutting tools due to regular operation. The most common type of tool wear is flank wear, in which the edge of the tool that is in contact with the material being cut erodes. As the cutting edge erodes, it becomes dull and cannot cut the workpiece as effectively, leaving behind a rougher surface finish. There comes a point where the edge becomes too dull to make good cuts and must be replaced. If tool wear occurs very frequently, tools must be replaced more often and can lead to much higher costs. The three primary machining parameters that cause cutting edge erosion are depth of cut, feed rate, and surface cutting speed. The three primary machining parameters that affect tool wear are depth of cut, feed rate, and surface cutting speed. As you can imagine, if you take a deeper cut, more of the tool is in contact with the part, and therefore there are higher loads on the spindle and workpiece. Increasing any or all of these will increase tool wear. Again, with higher tool wear, tool life will decrease and require replacing tools at a higher cost. A cutting tool can exhibit three modes of failure from excessive usage and wearing of the cutting edges, and they are temperature failure, gradual wear, and fracture failure. Temperature wear results from excessive heat generated at the cutting interface and above the operating temperature of the tool material. Fracture failure is caused by high forces on the tool that are a product of the high feed rates, cutting speeds, or spindle loads, and can cause the tool to shear and break in brittle failure. Finally, gradual wear occurs through normal use of the tool under desirable operating conditions. This failure mode is what this lab focuses on. Aside from observing lower quality parts after they've been machined, analyzing the change in tool geometry is the best indicator of tool wear. We do this by measuring the tool edge radius and diameter. Measurements are taken with software that will be introduced in just a bit. During the slot cutting experiment in section 4, multiple passes were taken into the material, and with each pass, the tool wore and increased in edge radius. Following that, the tool images from the digital microscope will be analyzed for wear. Slots are the best example cut to use as they engage an even amount of the cutting edge area of the tool and show cutting effects on the entrance and exit sides of the cut. To measure the edge radius and tool diameter values, we use a digital microscope to capture images of these critical features. We will measure these features before and after the cut in order to compare the changes. ImageJ, an open source image analysis software, is used to analyze the images collected from the microscope. These images will be supplied to you so that you can analyze and draw conclusions about the effect different process parameters and workpiece materials have on tool wear. Please refer to the Section 5 ImageJ procedure in the folder for steps on how to accomplish this.